Hello everybody and welcome to part 4, how to identify minerals. Now, conclusively, the only real way to identify minerals is to use chemical analysis, thin sections, which I do have the ability to do here, or X-ray power diffraction. We can't do that here, but what you see behind me, I wrote down all the ones I could think of. Here are 15 things that you can use to identify minerals, and you can use these to cross-check with others, to rule things out, or to clue you in into new ones. I am just going to touch on most of these. There are a few I want to demonstrate here for you in the lab, because I think it's kind of cool how this actually works, how you can use the physical properties of a mineral to identify it without the need for electron microscopes or X-ray diffraction or anything like that. Now granted, there are some minerals that are so similar that you need those things to differentiate, but with common rock forming minerals it's not that way. Alright, first I'm going to just really quickly touch on luster. This is not a definition. I'm not going to show you definitions, I'm going to verbally give them to you. These are words, modifiers you would use to describe luster. Luster is just the physical appearance at first glance of the light reflected from the rock, essentially, or mineral, whatever it is. You can see here I have metallic. This piece of copper you guys have seen before, this has a metallic luster to it. It looks like a chunk of metal. This rock here, it's not a mineral, but minerals can look like this too, is dull. It doesn't shine, it doesn't gleam, it doesn't sparkle, it doesn't do any of that stuff. Now we can have combinations as well. This piece of copper is definitely metallic luster to it. This one also does, but not as brightly. It's kind of dull, so you could describe its luster as metallic and dull. I think that's all I'm going to say about luster. Hardness. This one we're going to spend a little bit of time on, because in the lab or in the field you would use something called Mohs hardness scale, and I'm going to explain this a little more in detail here. Another great mineral test is something called hardness, and we usually use Mohs hardness scale. What you need to understand about this though is that it is a relative qualitative scale. What does that mean? That means it does not have specific measured values attached to it. It's basically like me taking these two pens. They both have a set thickness. This one is probably, we'll just say, 1/4 of an inch wide thick, and this is more like 1/2 inch here. So instead of saying 1/4 inch, 1/2 inch, we would say this is a 1 in thickness and this is a 2 in thickness as our standard. And that's what the Mohs hardness scale is. What you see on it is you see things like quartz, which will scratch talc, and then you see things like diamonds, which will scratch quartz. What do I mean by scratch? Well, you take two of these minerals and rub them together and one will scratch another. Now there are other things that have equal hardness. These minerals are just the standards. All right, and you can see on to the right here, there are everyday things you can use to test for hardness, because they too have a hardness standard. You can actually purchase scratch kits at an ordinary hardware store. I have one, but mine is not from a hardware store. It's actually from a mineral website online. So I guess a mineral dealer, if that's a thing. It has a list in there that isn't just the tools. If you go to a hardware store, it's just going to be the tools, and they're exactly the same ones. So, you know, it is, so you can use either or. How you do this is you take the tool, whatever that tool is, in this case my actual picks, this is a pick from the hardness test, and you use it to scratch something. You draw it over with a moderate amount of pressure. You don't want to dig in deep, and you don't want to do it so light nothing's going to happen. It's just a little bit of pressure to do it. And if it scratches the mineral is at least that hard or harder. If it doesn't scratch, the mineral is still harder. Okay, if the tool actually scratches the mineral, that doesn't necessarily mean the mineral's that hard. It could be softer than that. You got to find the tool that minimally scratches it. For example, if I scratch it with a number 8 and that scratch is pretty deep, I need to go to a 7. If I scratch it with a 7, it's still pretty deep, I go to a 6, and if it doesn't scratch with a 6, well, it's somewhere between a 6 and a 7, probably about. You can assume 6.5. A lot of times we'll try to read in between the lines a little bit. The use of this hardness test is actually pretty useful in eliminating minerals within a rock that has a diverse number of minerals in it, like a granite or something like that. But there's something you need to remember. This is a hardness test, okay? This is not a strength or a toughness test. Diamond, the defining number 10 mineral, is the hardest thing on this scale. You cannot scratch a diamond with anything else on this chart. That does not mean a diamond is indestructible. Like I said, it's not a strength or a toughness test. Even if diamonds were as common as, say, nails were, or we'll say steel in general, because a nail is essentially about the same hardness as steel, we wouldn't build buildings out of it. Why? Because diamonds fracture, and we're going to get into this in a later episode. You can actually break a diamond by hitting it with a hammer, okay? Because it's not that strong, even though it is very hard. Okay, so these things are not synonyms. All right. We're going to spend a little bit of time on this one too. Number 3, reactivity. And what we mean by this is, how does a mineral react, usually with weak acids? How is there a chemical reaction between the mineral and some other sort of substance? And common ones are weak acids like vinegar or dilute HCl. You've seen this before. It's the chemical formula for hydrochloric acid, but you don't use what you get in the store, like muriatic acid, that's too strong. I do buy that and I mix my own. I dilute it into a weak 3 to 5% solution, and this is commonly what you would bring out in the field with you to test limestones, and a 10 to 15% HCl, which would be more for your like dolo stones, your dolomites. There's more magnesium, less calcium carbonate in it. And I'm going to show you how this works. Hopefully you guys remember this calcite dominated geode here. Now what's going to happen is calcite reacts pretty vigorously even with weaker HCl. So what I'm going to do is I'm just going to put a couple of drops on what I suspect is calcite here, and it should fizz. Not only can you see that, but you can hear it. Let me do it again. Hear it? That's what we call a vigorous reaction. And when it comes to calcium carbonate or calcite, that is a defining property. The fact that it fizzes like that with this 3 to 5% weak HCl, hydrochloric acid, tells me definitively that's what it is. I'm going to speak about numbers 4 and 5 here together. I've already kind of talked extensively on crystal structure. That has to do with the 6 or 7 crystal systems. I don't have enough to show you anyway, although I do have Ward's mineral boxes. This is my 2 of 2, and there's the list of minerals in this box, but for sake of brevity and whatnot, I don't want to bust all these out and talk to you about these. I will do that at some point in the future, just on my channel in general, probably. So let's put that down. If your teacher has sets like that, they can show you the minerals and go through the systems with you in detail and all that stuff. But I am going to talk a little bit about crystal habit. Now, these are kind of tied together anyway. Crystal habit, in order to determine that, you need good crystal development. And with something like this, which I've shown you plenty of times before, and you're going to keep seeing, the quartz crystal, that is obviously good hexagonal crystal development. We could describe this as prismatic and even as columnar. It almost forms like a column, but you don't need to. Prismatic's good enough. This is a good prismatic crystal. These crystals, which you're going to see again, this is from Tennessee. Just like you can have 2 different lusters, you can have 2 different type of habits going on. The crystals in this, the brown ones I'm talking about here, are prismatic to tabular. I don't have anything that's dendritic, but dendritic would be like a river, like a dendritic river system. It would branch out. Pyrite will do this on occasion, and looks like the branches on a tree. Needle-like, those are very thin, pointy crystals, and those minerals are hard to keep without breaking. I don't have any. Bladed would be something like kyanite. It's kind of a squished, long, prismatic version to tabular, except it's really long. Looks like a knife blade, essentially. Fibrous, these would be your asbestoses, stuff like that. And like I said, tabular is pretty much stuff that kind of is prismatic, but may not be, maybe columnar, but may not be, so we kind of use it for that. And there are some that have no crystal habit. This doesn't really have a crystal habit. It's just blobular or globular. You could say that about it, but that falls under something else. When identifying minerals, individual minerals and crystals like this, it's pretty easy to pick out habit. But when you've got something like this rock here, it can be a little difficult. As a matter of fact, crystal habit, the dark black minerals in this, led me astray when classifying this. When I was talking about luster earlier, metallic luster, the black in here does have a metallic luster, and I should have gone with that, but I didn't. The habit tricked me, okay? And it led me to think it was something else, but it is a metallic mineral, and I'm going to show you which metallic mineral it is here in a little bit. Number 6, failure. This is how a mineral would essentially fall apart if I were to hit it with a hammer. Now, I don't want to break any of my minerals, so I'm not going to do that. But I'm going to talk about the first part. There's two. The first is fracture, so minerals can fail when I hit it with a hammer via fracture, and these are some of the patterns that develop. Hackley is essentially like, it's jagged, like it would be if you shattered some glass. And actually, this quartz crystal failed Hackley on the bottom here, as you can see. But quartz can also fail conchoidally, and this is more common. The minerals in here have failed conchoidally. You can kind of see it right here on this crystal. If the light reflects right, you can see the conchoidal fracture, and that means curved fractures. And these also reflect into rocks, so you can use the same patterns. Rocks will fail happily or conchoidally, what we call that jointing, but those are talks for other times. The last part is splintering. I don't have an example of that. That's basically like when wood splinters. That would be the same way. You can think of it that way. The second and usually more common way a mineral can break is via cleavage. Anyway, here are 3 of many different types of cleavage failures: planar, cubic, and octahedral. What you need to get out of cleavage failure when pertaining to minerals and rocks, cleavage is a very neat and clean break, as this GIF here shows you. That's what you need to get out of it, as where fractures tend to just be shattering, if you will. And we are going to come back to these an entire episode in and of themselves, so let's move along. Number 7, and one of my favorite, is fluorescence. I'm just going to touch on this on the board here with you because I want to show you what it actually looks like. Fluorescence is a mineral's ability to change color brightly when hit, usually with ultraviolet light, either short wave or long wave. I am going to show you a long wave example that's supposed to be an LW. What causes a mineral to fluoresce? Basically, there's 2 reasons why it will. Because it's an intrinsic property of the mineral. What that means is because of the mineral's chemical formula, the elements that make it up cause it to fluoresce. All right? There's no outside factor. It's a non-changing property of the mineral and can define it. Or because of activator elements. These are impurities within the mineral that causes it to fluoresce. Now I'm going to show you a mineral that will fluoresce in long wave, and it is an intrinsic property of that mineral. And that mineral, I've already mentioned, is called sodalite. Remember earlier when I showed you this piece of sodalite from South America? and how blue it is. And I said it can also be white or slightish pink, but this is a pure blue version. So I've turned the light out, and now I'm hitting it with long wave ultraviolet light. See that orange? Now, it looks a lot more impressive to the eye than it does here, but that is an intrinsic property of sodalite. Right? It fluoresces that orange and bright orange. Now, against the dark blue, it doesn't stand out as much. Although this particular specimen, being bright orange with on dark blue mineral, kind of doesn't fluoresce, and the camera doesn't do it justice. But wait, I've got white sodalite. Now, these rocks don't look very impressive. They're kind of light gray, dull. They're granitic rocks. They are not granites, and this is a rant for another time. But if you have sodalite, which is called a void in a rock, you cannot have quartz, and granite by definition has quartz. They look granitic in appearance, and as you can see, this one with those black minerals that fooled me, that's here too. So let's turn the lights out and see what we get. Okay, let's do the one that the dark minerals fooled me, and you'll see there is some orange in here. There's not a lot. It's not pervasive, but there is some. All right, so this has a little bit of sodalite. Now let's go to these. Look at how those fluoresce. These are loaded with sodalite. These gray rocks, the boring gray rocks, fluoresce this awesome bright orange in long wave UV. So these rocks have a lot of sodalite in them, and these are pulled from the shore of Lake Superior in the Upper Peninsula on the Keweenaw, not too far from our cabin, and these were brought down by the glaciers and the waves from what we call the Coldwell Complex in Canada, which is off the northeast corner of Lake Superior. These were found south middle on the shore. Just real quick, I'm going to touch on number 8 here, density. You can also use something called specific gravity, which is kind of related, except it has no units attached to it. But you're more familiar with this, I'm sure, so we'll go with density. And this is the equation for density. This is my rho. It's a Greek letter, equals mass over volume. And in science, when we take measurements, we generally use what's called SI units, or what you may think of when someone says the metric system. If I get a density, it'll be some number that's this X in grams per centimeter cubed. And there's other advantages to doing density using metric instead of things like ounces and pounds, because the beauty of the metric system, 1 cubic centimeter at what we call STP, standard temperature and pressure, is equal to 1 milliliter of water. So the two are interchangeable, because when you run a density test, you'll get your mass from a scale, and you don't need a lot to do this. And you'll get your volume via graduated cylinders or graduated beakers. That just means, graduated just means they have marks on them. But these are all milliliters. But you need something in centimeters cubed. Well, if my mineral that I dunk in the water displaces maybe 7.5 milliliters, that's equal to 7.5 cubic centimeters at STP. This beautiful translation does not happen in the standard imperial system. Number 9 is something we call streak. And basically what that is the color of the mineral in powder form. And we determine that very simply using non-glazed porcelain plates. These are for lighter minerals, the dark one, and these are for darker minerals, the white one. Now, even though, and I'm just going to tag along color here a little bit too, and I'll touch on it again later. Color isn't really diagnostic of a mineral. Okay, see this clear piece of quartz here? I can do this for you. It's not always clear. I've already touched on this. Quartz can be white, which is referred to as milky quartz. It can be purple, which people who collect gemstones refer to as amethyst. It can be gray, which is smoky quartz. It can be pink, which is rose quartz. So color isn't really diagnostic of a mineral. It can vary, and calcite can be any color. It's usually clear or white, but it can be any color. I've seen brown calcite. I actually have some in a bucket somewhere. But anyway, the streak is not that flexible. Most minerals will streak their primary color, like quartz doesn't really have a streak, it's not a good example, but calcite and most minerals will streak white, but some don't, especially more metallic ones. And even though something like this, which I'm going to streak for this banded iron formation, this is the only sedimentary rock Earth no longer makes. It's Precambrian. This is from the Upper Peninsula. I cut and polished this. But you can see not the red, that's jasper. That won't really streak well. We're going to streak the gray. And you might think, well, the mineral's gray, so the streak's going to be gray, right? No, it won't be. Okay, so here is our piece of banded iron formation, or BIF, B-I-F. And we are going to streak the hematite, the gray part. Now watch what happens when it streaks. It's not going to be gray in the case of hematite. It's reddish brown. Number 10, tenacity. I'm not going to spend too much time on this because it's not really a test I do. It's kind of related to failure, except you don't need to actually destroy the mineral to look for tenacity. You can destroy the mineral in the process. Like if I take this quartz and I start bending it, well, with a machine, because my hands, I can't do it with my hands, eventually it's not going to flex, it's not going to stretch, it's not going to just kind of form into my hands, it's going to break. And we already know it undergoes Hackley or conchoidal fracture. This is another Hackley fracture. So the vast majority of minerals just break. Malleable, let's grab our copper again, but let's grab this one. If I were to put a metallic mineral on the table and just let it sit there on the edge, and if it was a softer mineral, and this copper holds its shape really well, over time it might bend a little, or if I lightly tap it, I can get it to stretch a little bit. That's malleable, and most metals and elemental minerals are malleable. Flexible basically means if I bend the mineral, like if I can do it with a machine or whatever, and then I relieve that stress, it should go back to its original shape. There aren't too many minerals you're going to run across that can do that. Elastic. I'm just going to do this with silly putty. Silly putty is not a mineral. It's not even really a solid. I mean, it can be. But silly putty also has a mixture of properties. It's brittle if I pull it really fast, but if I pull it slowly, it's elastic. That's what elastic would be. There's no mineral that's that elastic, but there are some that will stretch. You're not going to run into those either. So I think I'm done talking about tenacity. Okay, number 11, magnetism. I'm going to do a demonstration here for you in a little bit here, but first I just want to talk about it for the purposes of a quick identification in a lab setting. Basically, magnetism is the ability to act like a magnet. So if the mineral can attract a piece of metal, or a mineral's ability to attract a magnet. So the other way around, you have the mineral sitting there, you put the magnet on it, and it sticks. All right. Now, I'm going to show you two separate minerals. One is hematite, Fe, which is iron, 2O3, oxygen, and it forms hexagonal crystals. That's a crystal system. And magnetite, which isn't chemically much different, the chemical formula is Fe3O4, and it forms isometric or cubic crystals. We refer to that system as either isometric or cubic. Now, one of these is magnetic and the other really isn't. And I'm going to show you here real quick. I'm going to show you the BIF again and that odd rock where the dark mineral confused me. Okay, this is just a cheap garden variety magnet that actually came with my Hardness test kit. We're going to use the banded iron formation again, the BIF, and remember the gray is hematite. Watch what happens when I put the magnet on it. It stays, right? Nah. Falls off. Hematite isn't very magnetic, even though it has a lot of iron in it. And this guy here, this granitic looking rock
which has sodalite in it. What happens when I do this? Now remember I said these black minerals kind of confused me. Their crystal habit misled me. Well, after I streaked it and realized the streak was gray and not reddish brown like hematite, I decided to do this. See that? Not something you'd expect from a granitic looking rock. But that dark black mineral has enough magnetite in it to keep that magnet on even when I turn it upside down. So you can sometimes find things out about rocks and minerals in places you wouldn't expect to find them. Sometimes you can find out things about rocks and minerals in tests that you normally wouldn't think to conduct on them. Number 12, visual optics. Some of these are real useful, some are not. There's basically two parts. You have light penetrative. Don't worry about these first two. These are the three type of light penetrative visual optics you can use to classify a mineral, but the only one I have an example of is labidorescence, which is more commonly known as iridescence. The plagioclases that have almost no K-spar in them will tend to iridesce. And I have a clock made out of labradorite, hence where the word labidorescence comes from. And basically what this means is you get a change in color when you move the mineral or rock or whatever it is under the light. All right, bubbles that you blow in the air, you know, you'll see those colors on them. That's iridescence as well. Light directional manipulation. Basically, that's refraction. That's all that is. And in this little demonstration here with my butter knife in dipping it into the water, what you see if you look at it from different angles, the object not only can look bigger or smaller, but it can look offset, or in some cases even look like there's two of them. There is a real common mineral that will express that double thing called double refraction. That word, and I hope I spelled it right, I can't even pronounce it, is the technical term for it, but everyone I know says double refraction. Calcite does this. If you have a mineral that will fizz with 3 to 5% HCl and display double refraction, you unquestionably have calcite. You can stop right there. All right, these two are not related, but I'm going to talk about them in the same breath because I don't need to speak very long about either of them. I've already said color is not really diagnostic of a mineral. Some minerals are always one color, like kyanite is always blue, but if you have a blue mineral, that doesn't mean you have kyanite. Sodalite can be blue. Pyrite almost always is a golden color, hence the name fool's gold that some people use to describe it, but because you have a golden colored mineral, doesn't mean you have gold. Okay, so in sedimentary rocks, color can be helpful to clue you in as to what type of minerals are there, but those are talks for other times. Radioactivity, I know everyone freaks out when they hear this word, but it's not that big of a deal. The vast majority of Earth materials to some degree will be radioactive. Now most of these things give off what we call alpha particles, which your Geiger counter can detect, and alpha particles, your clothes will stop, your skin will stop. It doesn't penetrate into you, so it's harmless. But you really need a Geiger counter to detect how much radiation something is giving off. This is a piece of Mississauga protoquartzite from Canada, and you see its yellowish color to it. It has uraninite in it, what we used to call pitch blende. It's a mineral that's radioactive because it has uranium in it, but I can safely hold it in my hand. I'm not going to get cancer or anything like that from it. The 15th and final thing we are going to talk about is texture, also known as state of aggregation. I've seen that written before, but you can just use the word texture. If you're writing in notes in the field, you're going to write this, not this, all right? And these are 5 basic types of textures. When describing a mineral, we also use texture for rocks, just like we will fracture and cleavage, but those are talks for other times. We use a lot of the same words. You have something that can be granular in appearance. A granular mineral will look basically like a sandstone for all intents and purposes. It looks like that. Crystalline, this is how we abbreviate crystalline, XLN, or crystal would just be XL. That would be something like this, which is a nice granitic rock where you can see well-defined crystals on it. And we have banded, which technically this is not one mineral, it's 2. We have the gray hematite interbanded
with jasper, which is really just red chert, which is a mineraloid, and hematite is a mineral. So maybe we do just have one actual mineral in this rock. Botryoidal, or I just say globular, would be something like this piece of copper. Oolitic. That has to do with carbonate rocks. I'm not going to get really into detail with that. It's very rounded carbonate grains. Those are talks for other times, really, and I don't really have anything to demonstrate it for you. And piezolytic, or piezolites, are just really large oolites. So it's a size thing. Now, of course, these are just some quick tools that are really accessible in any sort of basic geology lab setting. There are other more complicated pieces of equipment I have here. Like I do have microscopes where I can see magnification up to 1,000 times. But 50 times is typically what I need. So I have a lot of magnification equipment and other stuff to determine this. I don't have the ability to do electron microscope scanning, nor can I do X-ray diffraction. Those machines cost hundreds of thousands of dollars. But anyway, I think that's it for this episode, and I hope you guys learned something.